Hello, welcome to the fourth video in my sequence on differentiation, and this video is going to look at stationary and inflection points. And we're going to start off with a recap of what they are and then look at a typical exam style question. So to begin with, I've got a curve here, it's a cubic curve, and we're just going to take a recap of what the first and the second derivatives are. So we're going to look at some graphical aspects before looking at stationary and inflection points. So the first derivative represents your gradient. So if it's positive, it means your function, that is the y values of your function, are increasing. If it's negative, then your function is decreasing. And if it's zero, then your function momentarily is kind of what we call stationary. So its y values aren't changing. You might describe that as the function looking flat. You can think of the second derivative as being the behavior of your gradient. So if your second derivative is positive, then your gradient is increasing. That means the line of your graph is getting steeper, but it's still positive. Okay, and the second derivative, when it's negative, it means your gradient is decreasing. So the line is getting less steep, the gradient is going down. So if we take a look at that on a graph here, so if I look at my first derivative, then if I read this graph from left to right, to begin with, my first derivative is positive because my function is increasing. The y values are getting bigger and bigger and bigger until I reach this point here, where we've got a turning point or a stationary point, and this is a maximum. So here our first derivative is 0 because our function, the y values, aren't increasing or decreasing. For a very small period of time, they're staying the same. Then our function starts to decrease, it's going down, the y values are getting smaller. And it keeps doing that all the way until we reach our minimum down here, where again our gradient is 0 here. So we've got a turning around point, a minimum. If we were to draw a tangent, it would be horizontal. And then the function, after it's turned around, starts increasing again. So our gradient is back to being positive. If I think about the second derivative, then in the first segment of the graph, our gradient is positive, but the graph is getting less steep. The gradient here is bigger than the gradient there. It's going down. The gradient is decreasing. So our second derivative is decreasing. It's negative. The name for this type of shape is concave down. And that continues even after our turning point. The gradient there is 0 and then it becomes negative. So it's still decreasing all the way up until roughly about here. Because at this point, the gradient is still decreasing, but it starts to get still negative, but a smaller negative number. The line, so if this is a gradient, say, of -1, here we've got a gradient maybe of -0.5. It's getting smaller, the gradient. The number is getting smaller, but it's negative. It's getting closer to 0. So at this point, our second derivative switches. Over here, the gradient is a big negative number, becomes a smaller negative number, it becomes 0, and then it starts increasing again. And it gets steeper and steeper all the way in the rest of the curve. And this shape is called concave down. And so in this graph, we've got, for the second derivative, basically two types of behavior. For the first half, it's negative. For the second half, it's positive. And at this point where it sort of stops, well, transitions from concave down to concave, sorry, I wrote down there, concave down to concave up. Here, our second derivative is 0. And this is what we define as an inflection point. So on this graph, we had a maximum over here, a minimum over here, and they're both local maximums and minimums because this function does get smaller and larger if we were to look further ahead. And then we have an inflection point in the middle. And we can kind of take that behavior of a graph and turn it into some rules, which is that at a maximum point, our first derivative is 0, but our second derivative has to be negative. While at a minimum point, the first derivative is also 0, but the second derivative is positive. Meanwhile, the rule for the inflection point is just the second derivative is negative. The first derivative could be positive or negative, we don't actually know. And we can take these rules and apply them in a question without having to do a full graph, without having to think about the behavior everywhere. We can just take these rules and use them to focus in on maximums, minimums, and inflections. And if we can find those, it makes sketching graphs fairly easy, which is the main reason that we might be interested in finding out what they are. So let's look at an example. So a curve has, oops, and I realise I've got part of it still written here. A curve has equation y equals x cubed minus 6x squared plus 9x. Find the coordinates, so part A, find the coordinates of the stationary points. So stationary points means maximums or minimums or possibly a stationary inflection. So what we want to do is to find the first derivative and set it equal to 0. Using that rule up there, maximums and minimums, first derivative is equal to 0. So we'll do that. So dy by dx would be 3x squared minus 12x plus 9. That's our first derivative. And we want to set it equal to 0, and we want to solve it. So you may want to use the quadratic formula here. If it was on a calculator paper, you could go ahead and just solve it in your polynomial solver. It does actually, it's easier than it appears, because what we can do is divide everything by 3, and we'll find we actually get a quadratic which factorizes. Because I'm looking for two numbers that multiply to make plus 3, but add to make minus 4, and those two numbers are minus 3 and minus 1. So I get two solutions from here. X is 3 and x is 1. It asks me for the coordinates, so that means the x and the y. So when x is 3, y would be 3 cubed minus 6 times 3 squared plus 9 times 3. So 27 minus 54 plus 27, which actually comes out as 0. And the other one, when x is 1, y would be 1 minus 6 plus 9, which is 4. So 1, 4. And we have our two coordinates for our stationary points. Part B then says justify whether the points you have found are local maximums or minimums. And this is where the second part of that rule comes in. This is where we're interested in the second derivative. There is also a first derivative test that you can do, but is usually a bit more time consuming. So the second derivative test is normally the quickest one. because from these coordinates, I don't know which of them is a maximum and which is a minimum. So what we can do is we can find the second derivative. So that would be 6x minus 12. So I've taken my first derivative and differentiated it again. Make sure that you don't take the one where you've divided it by something or done some manipulation on it to solve an equation, because it will lead to the wrong answers. You need to make sure you use the original first derivative. And we're interested in when x is 3 and when x is 1. So we get two values for our second derivative. Since this one is positive, then we are a minimum. So our coordinate of 3, 0 is a minimum. And since this one is negative, then we are a maximum. So our coordinate of 1, 4 is a maximum. So we saw up there, if the second derivative is negative, maximum. If it's positive, minimum. Actually, what we can do, let's take hold of these ones and just move them down to the side here, make it a bit easier to refer to them. Okay, right, next part, find the x coordinates of any points of inflection. So our rule for inflection points is that the second derivative is 0. Now, we already know the second derivative from part B. It's 6x minus 12. So we can take that equal to 0, which means x is 2. And we've only got 1 point of inflection. So we didn't know from the question if there was 1 or more than 1. It turns out there's only 1. And then part D says verify your answers to part B using your GDC. So this is where you might get asked to do a sketch of a function or to use your GDC to find some of these things. So we're going to check that. Just grab our GDC. So in our GDC, we want to go to menu and graph. And we're going to type our function in x cubed minus 6x squared plus 9x. We're not really sure what size window we might want. I can see that my maximum minimums are 3, 0 and 1, 4. So before I sketch it, I'm going to press Shift and then I'll get this option for V window. And I'm just going to put it on standard. So F3 again, underneath where it says standard, which will put my calculator with axes of minus 10 to 10 for X and Y. And then if that's not the size I want, I can change my mind afterwards. But that's usually a good place to start if you're not sure how big your graph needs to be. And actually that works. I can see my whole function there. So let's check our coordinates. We're hoping that the maximum is at 1, 4 and the minimum is at 3, 0. So to check those, we're going to choose gsolve, so F5. Then we'll check the maximum first, so that's F2. And we can see x is 1, y is 4. That agrees with my coordinate there. We do the same thing again, F5 and then F3 min to find the minimum, 3, 0. That agrees with us as well. Our calculator won't find the inflection for us. There are other ways of going around it, but usually we're just looking to check the maximum and the minimum. If I look at it, I got my inflection as x is 2. And if I look at this picture, we've got the first half being concave up, the second half being concave down. Sorry, wrong way around. First half being concave down, second half being concave up. So x is 2 seems a reasonable location for that inflection point, somewhere between the maximum and the minimum. So what I suggest you do now is take a look at some exam practice questions. Okay, to try if there's a lot of different varieties they ask about inflections, turning points. It might be using a GDC, it might not, but that is my suggestion. And then see if you can have a go at those ones. Okay, stay tuned for the next video, which is going to be on optimization.